So let's review from the previous class. In the last class, first I have defined something called as stress, which is limit delta A tends to 0 delta F by delta A. This is for the 1D, which is represented by sigma. This is for the 2D, sigma tilde. I have defined it as sigma 11, sigma 12, sigma 12, sigma 22. It is symmetric form, and sigma ij is equals symmetric form sigma ij, where sigma ij where I is plane direction, plane normal direction, and j is component direction, and sigma ij is symmetric as delta is to 0. Can you hear me? Hello, can you hear me? Yes, okay, great. Audio is not audible. Okay, I'll try to increase it. I'll try to increase the audio. Is it fine now? Can you hear me? Okay, okay. Let me start.
It is okay with your audio. I think there is a problem with the Ramchandra College of Engineering.
Okay, okay, that's great. So then I'll continue. Yeah. So
if there is any problem, I'll put the message. Okay?
Sure. Okay, great. So let me continue then. So then we defined the one-dimensional stress in that manner and two-dimensional stress in this manner, 2D stress. Similarly, the 3D state of stress is defined as sigma 11, sigma 12, sigma 13, sigma 22, sigma 23, and sigma 33. The stress is symmetric because there are no body moments present in the system. Next, the second thing that we have reviewed in the last class is strain. And we defined for 1D case the strain as, we defined epsilon is equals to limit delta L tends to 0 or delta x tends to 0, delta u by delta x, that is also known as du by dx. Similarly, for 2D case, epsilon is defined as epsilon 11, epsilon 12, epsilon 12, epsilon 22. View file properties. So okay, so now the strain is symmetric. Strain can be written in the 2D as epsilon ij is equals to 1/2 of dou ui by dou xj plus dou uj by dou xi. Since this operator can commute in addition, so epsilon ij is equals to epsilon ji. So this is the reason of being symmetric, because we assume the strains are small strains. Similarly, in the 3D case, epsilon is written as epsilon 11, epsilon 12, epsilon 13, epsilon 22, epsilon 23, epsilon 33, and this being the symmetric part of it. Okay, so then, and this relationship is also known as strain displacement relationship. So that is the third part of it. And then the fourth point, what we discussed in the previous class, is stress strain relationship. The stress strain relationship, assuming that we are only in the linear elastic region, we said that according to the Hooke's law, sigma is proportional to epsilon. That is sigma, if you remove the proportionality by introducing proportionality constant, it is epsilon. So sigma is linearly proportional to strain, or stress is linearly proportional to the strain is what is there. This is for the 1D case. However, for the 2D or 3D cases, we said that sigma ij is proportional to epsilon kl. That means any independent stress is dependent on, is linearly dependent on, or linearly, we should not write dependent, proportional to strain, independent strain components. Independent. So this is what we have learned. So by introducing proportionality constants, we can say that sigma ij is equals to C I J K L epsilon KL. So this is your stress strain relationship for a generic 2D or 3D case, where for 2D IJKL will vary, will take the values from 1 to 2 for a 2D case. For a 3D case, I, J, K and L. So I, J, K and L will take the values from 1 to 3. So for a three-dimensional state, we can see that it is 3 values for I, 3 values for J, 3 values for K, and 3 values for L. So total of 81 constants are required. This is the full form of stress strain relationship that is there between the stresses and strain, even though what we have assumed is it is linear, elastic in nature. However, in most of the cases, you can see in most of the cases, what we study, we restrict ourselves to isotropic material. For the isotropic material, your CIJKL is defined as lambda delta delta ij delta KL plus plus mu delta IK delta JL plus delta JK delta IL. So where these two are called Lame's constants. One can express, so there are two independent constants, that is lambda and mu. So lambda and mu are dependent upon, as we all know, on two independent constants, that is E and mu, where E is Young's modulus and mu is Poisson's ratio. So either you can choose these two as your independent variables, or you can choose E mu as your independent variables, and you can express one another in terms of either lambda mu in terms of E and mu, or E and mu in terms of lambda and mu. So, and mu is also known as your shear modulus. That is the thing which will be there. So now this is what we have studied in the previous class. In today's class, today what we'll be dealing is the current topics. We'll talk about equilibrium or equilibrium equations. The next one I forgot to mention, maybe I will also discuss as a 0 point, that is plane stress and plane strain condition. Then once I'm done, I'll try to deal with the topics like method of weighted residuals. This is what I plan to do. If I have some extra, I will try to see, I will also try to cover your variational principles. If I can cover in this class, I will try to show that the governing equations you obtain from the variational principles is same as what you get from the method of weighted residuals. So in order to continue further, let me stop once here. If you have any questions from the previous session, I will take it and then we'll continue with the today's topic. Not getting any response, I'll try to continue with the today's topic. So first thing is equilibrium. So let me use an example of a bar to describe the equilibrium conditions. The first one, let's consider an example, a simpler 1D example of a bar. So bar is a member, as we have seen in the previous class, is a member which is loaded in the axial direction and it has a stiffness of E and a cross section which is A, whose length is given by L, and let's start measuring my distance from this point. So let me take a small differential element here and try to enlarge it. So if I want to enlarge this small specimen of small thing which is of dx, this small area length is of dx, let me enlarge it and try to show it here. So this is dx. Let me put this one as, since I'm doing a free body diagram at this place, let me have the force at this place is P plus delta P, and this side the forces are P, and let me try to, and let me say if there is some body forces that are acting inside the thing of a magnitude small p. Then we can write by summation of forces along x direction, that is my x direction is along the, this is my x direction, this is my y direction. Then I can say that this, let us consider this as positive. So P plus delta P minus this one as another P, this is thing, plus there is a body force that is acting in the system along the positive this direction, P delta x is equals to 0. This fellow and this fellow gets cancelled and we will end up with delta P plus P delta x is equals to 0, or I can write it as delta P by delta X plus small p is equals to 0. In the limit delta X tends to 0, we can write it as dp by dx plus small p equals to 0. This is our differential equation, or also known as our equilibrium. No, but what is P? P is the force. Force is obtained as sigma times A. This is stress, this is area, and this is force. And small p is load per unit length. Let me see if I got some message. Okay, it is not for me. Okay, so let me continue with this. Now, this is force is the load. This is the thing. But we have studied earlier that our sigma is given as E times epsilon. And we know that our epsilon is given by du by dx. That means if I substitute this into this and then this into this equation, then I can say that P is equals to E into du by dx A. This is my force. And I take this guy and then put this fellow in this equation, then I can say that then I can write it as d by dx of p. P means ae du dx plus small p is equals to 0. This is my equilibrium equation for the bar in terms of displacement, because the displacement term is here. U is your displacement, and this is the equation of your equilibrium, or also known as governing differential equation. So now let's try to simplify it or understand this equation. So how did we get it? This is obtained by taking, let us review it once. So we took a bar and try to see the equilibrium in small differential element. So we tried to zoom in and we wrote that if this is P, the other side would be P plus delta P, and this one is the body force or body force per unit length. And by summation of the forces, which is nothing but equilibrium, we showed that, and writing using make use of the stress and strain definition, we wrote that d by dx ae du by dx plus p is equals to 0. Here I want to hold on to a minute and want to say that where a is a function of x, that means your cross section can be non-prismatic. That means your cross section prismatic. So, and E is also function of X. That means your cross section or your bar is non-homogeneous. That means the equation what we derived was more generic in nature. But in most of the academic problems, we consider the bar is prismatic. If the bar is prismatic, we generally tend to write V as, let's assume, A or let's say bar is prismatic. Bar is prismatic and homogeneous. That means A, this means A is constant and this means E is constant, right? If A is constant, so a non-constant is you can have a tapered beam. Here, this is A is a function of X, it is not constant. Whereas if you have cross section remains same, this is A is constant. So A is constant, E is constant. Then my differential equation will become d by dx. Just because my A and E is constant, then that means it is not function of x. If it is not function of x, I can bring it out of this and keep it outside. If I want to keep it outside, then I can write it as A E d square u by dx square plus p is equals to 0. Now this is first assumption. Let's assume second assumption that no body forces. That means small p is equals to 0. In that case, AE d square u by dx square is equals to 0 is your governing equation. Or let's you can have p can be function of x or p can be function of u, p can be something else. So there are several other cases. So let's consider only two cases where p is already function of x and p is 0. These two are sufficient enough. Anything will fall under those two categories. So this is your equilibrium equation. So what we have developed here is equilibrium equation. That is what we have done in a generic sense. Now, this is what I have promised. Then I want to go back and to the previous section on the stresses and strain. Uh, okay, before I complete it, let me give another perspective of it, how to write it, this expression. The same expression, this can be written as if A is constant then I can write d by dx ae du dx plus p is equals to a d by dx epsilon du dx plus p is equals to 0. Now I'm getting little bit crazy and I will write it d by dx epsilon into du by dx is nothing but, sorry, it's not epsilon, my bad, this has to be e. So e into du by dx is nothing but sigma, d sigma by dx a plus p is equals to 0, or I can write it this fellow again as d sigma by dx plus p by a equals to 0, where p is body force per unit length. Let me define small b as small p divided by a, which is body force per unit volume. Because this is length and divided by area, so b should be body force per unit volume. So then I can write this fellow as d sigma by dx plus b equals to 0. Why did I write in this case? Let me tell you in 1 minute. So in 1D case, even though you write in terms of displacement as d square u by dx square, but if you want to write it in terms of stresses, then in terms of stresses, this is the better manner. Now, if I want to show you for a higher dimension, I can simply say that for 2D slash 3D case, the equilibrium equation is written as del dot sigma, which is a tensor, plus body force, which is a vector, is equals to 0. Simply, just by looking at this expression, I'm writing a 2D or 3D case as del dot sigma, which is operated on a tensor. So here sigma is a scalar, b is a scalar for 1D. However, for 2D and 3D, sigmas are tensors and b is a vector. B is a vector body force per unit volume in the x direction, in the y direction, in the z direction. So if you're not understanding, where b is equals to in the bx, by, and bz for a three-dimensional case, and sigma is nothing but sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 2, sigma 2 3, sigma 3 3, and it is symmetric. So this completes, this is the complete or 1D, 2D, 3D. It is the generic way how you tell it is. In any standard textbook, you will see that equilibrium as mentioned as del dot sigma plus p. Actually, I have to derive it in this manner. I haven't derived it in this manner. I'm just showing the 1D case and its equivalence onto the 3D, but one can clearly get this equilibrium equation in a different manner, but I'm showing a just cheap trick. It would be very similar to it, but you have multi-dimensionality. Force balance in the x, y, z direction will give you in certain manner. So, and here del is an operator, and del is an operator which would be dou by dou x a hat plus j hat dou by dou y plus j hat dou by dou z. So this operated on this tensor plus b bar will equal to 0. So th this gets in partial derivatives gets complicated. Even though I just looking at this d, I changed it to delta sigma to sigma tilde b to b bar. It will come in this manner, but the derivation took a different thing, but you have to start it at summation of forces in the x, y, and z directions. So with this, we complete our topic on the equilibrium condition. So we derived, this is the equilibrium conditions. So this is the equilibrium for anything. So this is for 1D, 2D, 3D is the simplest case. If you try to write this fellow in terms of displacement, it would look like in this manner. Simply assuming that A is a prismatic, bar is a prismatic and homogeneous. This is the simplest manner one can write your equilibrium equations. So we are done with our first topic today. So now let me go to the second topic, that is plane stress and plane strain conditions. So we know that any generic piece of a structure is, I'm just taking a piece of a slab which is three-dimensional in nature. But for suppose if this thickness of the slab and thickness T tends to 0, that means we are analyzing a piece of paper like this, a piece of a paper, right? In this case, you can assume that it's a plane stress condition. This is plane stress condition. Why we are assuming a plane stress condition? Because we don't want to solve in the third dimension when the third dimension thickness is very small compared to my longitudinal direction and the width direction. So both the longitude, if the longitudinal direction and the transverse direction is much higher than the thickness direction, you can assume it's an approximation you make that it is plane stress condition. So by assuming the plane stress condition, what are the things actually when you can assume this such a condition, not just by having t is equals to 0, the following things one has to have, but to assume, to simplify it as, let me write it down, to simplify a 3D to plane stress condition, plane stress condition. First thing is t has to tend to 0 compared to our uh, other dimensions, or we have to write t divided by length comma t divided by width is much less than 1. Okay, much less than 1 means this is your length direction and this is your width direction. The length and the width are much bigger than the thickness, then you can get, this is the first condition. Second, the second condition says that the loading, so now since there is no thickness direction, the loading should be also within the plane. loading is within the plane. What is the plane? This is our this is our plane, like a sheet of paper plane. And loading, that means whatever you are applying, tractions or displacements, has to be contained within this plane. They should not be acting in the, this is not, this is not there. You cannot load it in the transverse direction. The loading should be within the plane. Next, third one is no variation of stresses or strains, whatever you want to assume, in the thickness direction. You can clearly see that the thickness itself is not there, very small. So there would be no variation along the thickness. If you take a sheet of paper and we are saying that stresses and strains, if it is varying within that small thickness, if they are varying hugely, then you cannot assume it as plane stress. So if the variation of the stresses and strains are very small in the third direction, then it is okay. That means our sigma x comma y comma z is only a function of sigma x and y. There is no dependence, that is no dependence on z, where this is x direction, this is y direction, and this is thickness direction. Okay, so then you can assume it as plane stress. Further, since it is this one, the plane strain conditions will help you, will, if it satisfies all these things, it will make these things to be guaranteed. That is, because of above, you can assume it simplifies the study by following. Those are sigma zz is equals to 0. Next, sigma xz is equals to 0. And sigma yz is equals to 0. So these are the three things that are 0. Further, epsilon zz is equals to mu times so I should write it as, so anyway I will write it, sometimes I interchange exchangeably, I write between x as one direction, y as two direction, z as third direction. So next one is plane strain conditions. Plane strain conditions are like cross section of a dam. You know the dam, You know the dam is running. If I take one cross section of this dam, then I know that anyway here that this is the thickness direction. This is thickness. Now the thickness is infinity because dams are so long. Okay, so in this case, the top one, two, and three still remain same assumptions what we made above. But because of this, what we will get it is epsilon zz is equals to 0, epsilon xz is equals to 0, epsilon yz equals to 0. So this is what we'll be getting it. At this point of time, I will stop and ask if you have any questions that are there so that we can interact. Questions, I will try to continue to the next topic. You have a question? You can type it. If you have any questions, please type. Yeah, please type if you have any questions. Okay, since you guys are not having any questions, I will try to continue further. So what we have reviewed so far is we started talking about plane stress and plane strain condition. When you can, instead of doing full 3D analysis, you can invoke plane stress or plane strain. When thickness is 0, you can assume plane stress provided the thickness direction is very small, loading is within the plane, no variation of stresses and strain are there. So then you simplify it by these properties. So let me just again let me rewrite it here since I have not given you properly. T is large here. Next, loading is within the plane and no z variation in z, that is sigma x comma y comma z is only function of sigma x comma y. In that cases, your epsilon zz, epsilon xg, epsilon yz equals to 0. Because of it, sigma xg equals to 0, sigma yz is also 0. However, sigma zz would be e by 1 minus 2 mu 1 minus mu epsilon 1 1 plus something of this form is there. If I may be wrong in the expression, but yeah, next time I'll try to see if I made this expression wrong. So that means if you look at it for the plane strain condition, your stresses in the third direction are present, whereas shear stresses are not present. And if you look into your plane stress condition, your stresses are 0, and similarly your epsilon xg is equals to, sorry, xg equals to 0, epsilon yz is equals to 0, but sigma epsilon zz is not 0, and it is given by this expression. This is the quite important. So now, instead of 3D analysis, in 3D analysis you need 6 independent components, that is sigma 1 x. For 3D you need sigma xx, sigma yy, sigma xy, then you need sigma zz, sigma xz, sigma yz. But if you make plane stress or strain, these things are either zeros or they are dependent on something else. So it leaves only to be 3 are independent if it is plane stress or plane strain. However, if it is 3D, you have 3 plus 3. But if it is plane stress or plane strain, you have only total 3, because these things are interdependent, and either they are all zeros, or correspondingly their strains are also related in the certain manner. So this is the simplification you make so that you can analyze your 2D structure, a 3D structure in a 2D sense, since the other direction variations, the z direction variations are very low. With this we complete the plane stress and plane strain condition. Now I will start a new topic, which is the third topic of the day, which is method of weighted residuals. Now, in order to explain this, what I will do is, again I will take an example. The example in our case is again a bar. Let's say homogeneous and prismatic bar, that is E is constant and A is constant. This is our length, and it has been loaded by force F here, and the X is measured from this. So that is E is constant, A is also constant. That is what I'm assuming. And let us say the body force is given in such a manner that my differential equation, let's say, is of d square u by dx square. Let's say EA is equals to 1 and small p is equals to u of x. Let's assume. How? Because we are solving some arbitrary beam whose point load, whose body forces are dependent by through displacement function, and E times A is 1. Because I am solving some academic problem, I can always assume to be this. In that case, my differential equation will become something like this. And also let's assume the length is equals to 1. Why am I assuming? Sorry. I'm assuming in this manner because it is purely academic in nature. The actual problems may have different values, but to set an example, we are taking an easier problem, which doesn't give us a lot of problems. Okay, so now we know that at u, x is equals to 0, it is fixed. Okay, so that means u at x is equals to 0 is equals to 0, and u at x is equals to L, not u, du by dx at x is equals to L, A times E is equals to f. But we know that L is equals to 1, and let me also define f by AE is equals to by certain number. Let me call it as 1. Okay, there is no harm by assuming such kind of things. So that means my u at du by dx at 1 is equals to 1, and u of 0 is equals to 0. These are called my boundary conditions for the above bar, right? These are the boundary conditions. These are not mine. These are the boundary conditions for the above bar. So boundary conditions for the above bar. So let me now write it, what is called a boundary value problem. P P P is nothing but boundary value problem. A boundary value problem is a problem which has governing differential equation plus given domain plus on the domain we have boundary conditions. So our governing differential equation is here in this case d square u by dx square plus u equals to 0. Let's assume this is our governing differential equation. The domain is du dx is equals to 1, u is equals to 0 at x is equals to 0. X is measured from here. Here it is at x is equals to 1. So let's assume EA is equals to 1, E into A. So this is our assumption. So we are solving for this problem for a point load which is also 1, and this is our thing. So we have a domain. The boundary conditions are u of 0 is equals to 0, u x 1 is equals to 1. These are my boundary condition, all three together. So now I want to give, I know the solution of this problem. The mute is unmuted. Let me continue it. So the method of weighted residuals. Now this is our governing differential equation. This is our domain, and this is our boundary conditions. Now we want to seek solution for this, given this as the domain and this as our boundary conditions. So the traditional finite element methods are also known as method of weighted residual is what we learn. So what we do is, in this current thing, let's assume our u is our exact solution, is a function, is nothing but our approximation plus some error. So this is exact solution, this is an approximation, and this is error. So what we do is we assume our exact solution as a function of approximation and thing. We try to put back this fellow back in this governing differential equation, such that, so we know that d square u by dx square plus u is equal to 0, because this is exact. But now instead of exact, I want to keep d square u tilde by dx square plus u tilde is not necessarily equals to 0, because this is an approximation. This is an approximation. An approximation will not make this one equals to 0, and that is non-zero. So I can write this non-zero thing as, since it is not equals to 0, I will write this fellow equals to capital R, which is a function of x, because everything is a function of x, and this fellow is not equals to 0. Now that is, this R is defined as residue. That is, when approximation is imposed on governing differential equation, we get residue R. And it is like buying a lottery ticket. Not everybody who buys a lottery ticket will be the winner. So u of tilde is like like that. It's an approximation. So by, if we are approximating, and the chances that what we assumed as our approximation being exact is like a winning a lottery, it is very rare. So u may not be equal to u tilde all the time, so you may end up with residue, and the residue may be not equals to 0. Now in the method of weighted residual, there are certain ways we can deal with it to obtain my approximation. The first one is called collocation method, and the second one is least square method. The third one is Galerkin method, and the fourth one is method of weighted residuals. Method of moments. So let us review all these four methods, and using these four methods I will show you how to obtain my u tilde. Let's, even before attempting u tilde, I want to solve for u analytically. Why I want to solve analytically? Because this is an easier problem. But not always you can find an analytical solution. I guess we can find an analytical solution for this, and then we'll make approximation through this four methods, and then we'll try to see how the approximate methods are matching with the analytical method. So for that, let us solve this problem like analytically. That is d square dx square plus 1 is operated on u of x, that is equals to 0. That means we can find this one as d square plus 1 is equals to 0. Then we will get our general solution u of x is equals to e to the power of plus r m is equal, or you can whatever you want to call it, d is equals to plus r minus I, right? This will be the solution because d square is equals to minus 1, d square is equals to minus 1, then d is equals to plus r minus I. So e to the power of d1 x a plus b e to the power of minus ix. I can as well as write this as in terms of cosines, c cos x plus c2 sin x, because this is a general solution based on our things. So I'm writing u of x is equals to this. Now this is our, any form, whichever form you write, this is our general solution. Now what we do is, then we will try to get something like our solution for the given problem. For that we need boundary condition. The boundary condition says that u of 0 is equals to 0 and du dx of 1 is equals to 1. So let's make use of these two conditions in the above equation. So u of 0, if I substitute this in that, is equals to c1 cos 0 plus c2 sin 0, and this is equals to 0, but sin 0 is always 0. So c1 into cos 0 is 1, so c1 is equals to 0. That means c1 is equals to 0 is one thing what we have got. Next, du by dx at 1 is equals to, if I differentiate this du by dx, I know that since c1 is already 0, now I can write my u of x. Let me write it. After noting this, I can write my x is equals to c2 sin x du by dx is equals to c2 cosine x. There is something there, so I will be there. So, and if I evaluate at 1, so if I evaluate at 1, then this will become c2 cosine of 1. So that means, and you know that this is equals to 1. So that means c2 is equals to 1 by cosine of 1. That means my final solution u of x in this case is given by This is my analytical solution, sine of x by cosine of 1. Now let us use collocation method. Collocation method. In the collocation method, what we do is we will take the residue and we will make it to be 0 at certain places. Before doing that, we have to make approximation. So before that, let's make an approximation as u of tilde is equals to a naught plus a1 x plus a2 x square. I can keep on making bigger approximation, but I'm thinking that this is good enough for me. If it is not good enough, we can try it with the bigger things. Now, but this is a valid approximation provided it also satisfies the boundary condition. The boundary condition says that u of 0 is equals to 0 implies my a naught is equals to 0. Similarly, du dx of 1 is equals to 1 implies that a1 into plus 2a2 times 1 is equals to 1. That means my a2 is equals to 1 minus a1 divided by 2. So that means my u tilde can be defined as a naught plus a1x plus a2x square, where a1 is 0, sorry, a naught is 0, a1 is a1, and a2 is given by a2 is given by 1 minus a1 by half. So if I substitute this in this, then I will get a1x plus 1 minus a1 by 2 x square, that is equals to x square by 2 plus minus, okay, let me undo it. It is, let me write it in terms of a1. So if I take it a1 into x minus uh, x square by 2 plus x square by 2. So this is my approximation, but I don't know what is this. What is a1? A1 is determined using collocation method. Okay, let us see how it is being done. That is, first again, now in the collocation method, this is your a, whatever is the boundary condition, you applied the boundary condition. Instead of u, you have u tilde, and you have a residue which is a function of x, which will vary depending upon the position. So what is the residue? Let us find out what is the residue. Residue is d square u by dx square plus u tilde. So let us see if u is this one, du tilde by dx is equals to a1 1 minus x plus x, and du square tilde by dx square tilde is equals to minus a1 plus 1. So since we know this, I will come back, I'll put it, this is equals to minus a1 plus 1 plus a1 x minus x square by 2 plus x square by 2 is my residue. This is residue for the given problem. Now there is a residue here, there is a residue here, there is a residue here, there is a residue here. But how many unknown coefficients are there for me? I have only one unknown coefficient. Let me rewrite it again in a simpler fashion, which is a1 times minus 1 plus x minus x square by 2 plus 1 plus x square by 2 is my residue. Now I choose, this is a choice. Choice a user, and user can make. So what I'm making is, I want to make my residue at midpoint. This is the midpoint. Midpoint, let's say, is this one. Midpoint. The midpoint is x is equals to 0.5. The residue is equals to 0. That means I substitute in this 0.5. That means it is equals to a1 into minus 1 plus 0.5 minus 0.5 whole square by 2 plus 1 plus 0.5 whole square by 2. At this place it must be equals to 0. That means let me use a calculator at this point of time. Minus 1 plus minus 1 minus 1 by 2 1 divided by 8 is, did I do it correct? Plus 0.5. So plus 1.125, that is equals to 0. That means a1 is equals to minus of 1.125 divided by 0.625 divided by 1.125, and so that gives me, this is equals to minus 1.8. So that means my u tilde, which is equals to a1 x minus x square by 2 plus x square by 2, but I know what my a1 now. a1 is equals to minus 1.8, or we can write it as 9 by 5 x minus x square by 2 plus x square by 2. That is nothing but this is equals to minus 9 by 5 x minus of minus plus, so 14 7 by 5 x square is our solution. You can check it out. 9 plus 5 is 14. 14 by 5 and 14 by 2, so it's minus. So the u tilde in this case is given by this expression. This is an approximation, but we know that the exact solution is given by u is equals to sine of x by cos of 1. So this is exact solution, and this is how we have approximated it. So there is difference between the solution coming from the exact and from the things. So this is point collocation method. At this point of time, I would like to stop and then ask you if there are any questions from the audience. Least square method. I think you might have used this least square method even in your Excel or something in your life. So in a least square method, what we do is, if this is an exact solution and this is our approximate solution, this is approximation, and the solid line is exact, then we have a positive error, a negative error, positive error, a negative error. That means, let me show it. Say this is okay. I don't know how to undo it. Okay, let me use something else. I wanted to something and it went off something else. So okay, let me leave it in this manner. So let me restart a new page. The second method is least square method. In the least square method, if there is an exact solution and there is an approximation, let's see, the approximation is made using, so this is your approximation. So we know that this is positive error, this is a positive error, this is a positive error, and then square method, sum of error in the negative side has to be equal to in the positive side. So this area, this area, this area, if I sum it, has to be same as this area, sum of this area, and sum of this area. So that is what the least square minimization will try to do that. So for that, what we do is we take our potential pi, which is nothing but our residue times residue. So now when you take this potential, r can be positive, r can be negative, but r square is always positive because, for example, 2 square is 4, minus 2 square is also 4. So r into r is quadratic. Because it is quadratic, this potential is always positive. Now what I want to do is I want to minimize this potential. So what I want to do is dou pi by dou a, that is equals to, and I want to integrate over the domain. This is over the domain we are integrating. So that means integral of dou r by dou a, r will get it 2 times. So I can put 2 here, but anyway when I equate to 0 it doesn't matter. So it means integral of dou r over the, integrating over the domain, dou r by dou a I, a i's, whichever is I don't know, a i's, r dx is equals to 0. This is my method of weighted residual. So that means in a method of weighted residual, you have a weight, you have a residual, multiply it together and equate to 0. In the least square minimization, if you look at these two expression, your weight is nothing but dou r by dou a. However, in point collocation method, in point collocation, your weight is nothing but delta x minus xi equals to 0. In the last case, what we did was we chose, you call it as wi. So we choose wi to be delta or w1, whichever you want to call it as, x minus 0.5. So that has given us, after you substitute this into integral, we have got r of 0.5 is equals to 0. Because delta is a Kronecker function, the properties of it is the area under the curve. So let me, so let, I don't know, let just, I made a mistake. This is not equals to 0. This is equals to delta minus delta xi. So wi is equals to delta x minus xi. So this is the thing. So that will give you, when I substitute my delta function into this and integrate over the whole length, I'll get directly r is equals to 0.5. However, in method of weighted residual, my w is equals to r by dou a. So here how many a's I don't know. I don't know only a1. So I would write it as dou w by dou a1. So that means integral of dou r by dou a1 r dx, integrate over the entire length 0 to 1 equals to 0. If I enforce it, I I can get my things back. So let us see what is residue. Residue, according to the previous case, is given by, let me open the previous thing, file, open. In the previous case, we have seen that our residue is given by this thing. We have seen that our residue was given by a1 minus 1 plus x minus x square by 2 plus 1 plus x square by 2. Now if I do dr by d a1, I will get this is independent of a1, this is linearly dependent on a1, so that is equals to minus 1 plus x minus x square by 2. So in this case, now my integral 0 to 1 to r by 2 a1 r dx is nothing but 0 to 1 minus 1 plus x minus x square by 2 into, what is your residue? a1 minus 1 plus x minus x square by 2 plus 1 plus x square by 2 integral dx, and then that has to be equated to big 0. So let's do this thing and then we'll break for the day. So let me simplify it for you. 0 to 1 a1 times minus 1 plus x minus x square by 2 whole square plus minus 1 plus x minus x square by 2 into 1 plus x square by 2 dx. That is equals to integral 0 to 1 a1 a square b square plus c square plus minus 2 ab minus 2 ac plus 2 ac bc b sorry, ac is this one is plus, and this one is this is 3 by 2 plus I'm still not done. It is minus 1 minus x square by 2 plus x plus x cubed by 2 minus x square by 2 minus x 4 by 4 dx. So let's try to simplify it further down. This is equals to 0 to 1 a1. So this is 1. So the linear terms is minus 2x. Then quadratic terms are this and this. So it is plus 2x square. Then cubic term is minus x cube, and the quartic terms are x4 by 4 plus minus 1. Next, the linear term is this fellow plus x. Quadratic terms are this minus x square plus x cube by 2 minus x4 by 4 dx. Now let us integrate it. Now since we have simplified it, 0 to 1, now we are already integrating it. So is equals to a1 x minus x square by 2 plus 2 by 3 x cube minus x cube by 4 plus x power 5 by 20 plus minus x plus x square by 2 minus x cube by 3 plus x 4 by 8 minus x power 5 by 20. Evaluate at 0, evaluate at 1. So that is nothing but if I substitute at 0, this will be gone, this will be gone. So I will only end up with the first upper limit, which is nothing but a1 1 minus 1 by 2 plus 2 by 3 minus 1 by 4 plus 1 by 20 plus minus 1 plus 1 by 2 minus 1 by 3 plus 1 by 8 minus 1 by 20. So that means, let me do the simplification as best as possible. I'll try to do it quickly. So a1, so this is 60. To make it 60, this is 30, and to make it 60, so what should I 20 into 2, 40, right? Next, this is 15, and this is 3 divided by 60 plus this fellow is coming out to be 8. 8 is a very bad number, so then we need to make it 120. So this is minus 120 plus 60, next minus 40, next This is 8. So this is 30, 15, and this is 20. So it is 6.
Sir, Vishwanath sir.
So that means
Sir,
I can write this one as, if I take 1 over 60 as common, A1,
Vishwanath sir.
this is 103,
Vishwanath sir.
103
Sir, Vishwanath sir.
minus
Please share your
15
document.
is 58 plus minus 120 plus 60 minus 40 plus 15 minus 6. So it comes out to be 33.
Vishwanath sir. Sir. Vishwanath sir.
Minus 33 by 2 is the thing. So that implies, and this is equals to 0. So A1 is equals to 33 by 116. So this is A1 that is obtained by, so that means our U tilde using um, least square method is equals to 33 by 116 into minus 1. What was that? Minus 1 plus x minus x square by 2 plus 1 plus x square by 2. At this point, I will leave the simplification to you. So anyway, let's recall U tilde from collocation says that it is equals to minus 9 by 5 x plus 7 by 5 x square, whereas U exact is given by sine x by cosine 1. So this is an approximation, this is also approximation, but this is an exact value. At this point of time, since we have been carrying out for a long time, I will take a break and then we will continue this thing in the next lecture. So if you have any questions at this point of time, I would ask you to,
Vishwanath sir.
sorry. So anyway, let me show it to you again. So the method of least square method, let's have a review. So the positive error, the negative error has to balance the positive error. So in that case, pi r into r of x, which is the positive quantity, and I'm differentiating with respect to my unknowns to get my method of weighted residual or the equilibrium thing. So in that case, what it automatically, this reduction makes it as my weight is equals to dou r by dou a. So that means my in the point collocation, my wi was nothing but delta x minus xi. Since in the previous example we have taken x minus 0.5 as our delta function, it turns out to be our method of weighted residual condition will lead to this condition. However, if you want to do it using the collocation method, then in the collocation method, this is 0 to 1. The weight is dou r by dou a1 r dx. Why we are taking with respect to only a1? Because only a1 is not determined. All other things are determined after the approximation has satisfied the boundary conditions. So if I take my r from previous case as a1 minus 1 plus x minus x square into this, and if I differentiate this fellow with respect to a1, then I get my weight as equals to this thing. Then I take this weight here and this r here, integrate it. That means I substitute the above things here and then I integrate it. After all this kind of simplification which I have made it through, then if I find it out, you see that my a1 through method of least square method comes out to be 33 by 1116. 33 by 1116, if I substitute back in my approximation which is given above, then I can say that using the least square method, this is least square method. According to the least square method, my approximate solution for the same problem what we have defined is given by this value. And if I recall the previous example, which is collocation method, using collocation method, this is the solution what we have obtained. However, the exact solution also which we derived has shown us this. At this point of time, what I do is I would request you to plot the solution for the least square, plot the solution for the collocation, and plot the solution for the exact in your MATLAB or Excel sheet, and you yourself could find out how the approximations are differing from the exact things. If somehow you don't like this approximation, it is very rude, then I would request you to make a refined approximation by taking your new u tilde as a naught plus a1x plus a2x square plus a3x cube, and then ignoring the other order terms. So we ignore these things, assume another variable into the system. Then the method of weighted residual, you have to make r at, let's say, 0.5, and or let us choose something else. Let's make it r at 1 by 3 equals to 0 and r 2 by 3 equals to 0 will give you your a1 and a2, and a3 and a0 is already 0. This is already 0. A3 can be written in terms of a1 and a2. A3 is a function of a1 and a2 after using the boundary conditions. And similarly, you can write collocation method or least square method as dou r by dou a1 r dx equals to 0, dou a2 r dx equals to 0 will give you two sets of equation in terms of a1 and a2, and if you solve for it, you can determine a1 and a2, and if you determine a1 and a2, since a3 would be function of a1 and a2, a3 is also determined and a1 a0 is 0, then you will get a better approximation. Like this, you can keep on improving it. At this point of time, I would request if you have any questions, and then I'll take few questions and then we'll close the session. With respect to, initially we started with an approximation which only constitutes of this. Now I'm asking you to add another cubic term and take the new approximation. Then you will see that it may become much better. Even if this is not coming, then you will add up a fourth term and then you carry out your studies. As on you keep on adding the number of terms, you could realize that eventually all the things would give you a similar fashion. So at this point of time, if you have any other questions, let me know. Otherwise, we will end the session. Okay, since there are no other questions, what I will do is we will end the session today, and the next session will be on Wednesday. Sorry, today I was late by half an hour because my paper was there in one of the conference at Allahabad. So maybe by next week I'll be in my office during Wednesdays and Fridays. I'll keep my travel short. So thank you for the class, for staying extra long, and for accommodating for my delay. And see you next Wednesday. Thank you. Hello. Thank you for the class. We will meet in the next Wednesday.